I introduce you to strong acids, and I introduce you to weak acids. Okay? So what we just said with respect to strong acids, essentially, when we put them in water, completely ionize, meaning that all of the acid that we put in goes to form H3O+. Okay? So for example, if I had a strong acid, how would I know if I had a strong acid? How would I know if it was strong or not? So there was a table, there were 6 of them, right? So I talked about them all. It was like, oh, the halides, the hydrogen halides, and then there were some sulfurics in there, and nitric maybe. So there are 6 strong acids, and it would be important for you guys to know what they are. So HCl is 1, HBr is 1, HI is 1, HNO3, H2SO4, and then the final one is HClO4. HClO4, what is that? Oh, shoot. It's chlor. So chlorate is ClO3 minus. So what would ClO4 be? Perchlorate, right? So what would the acid of that be? Perchloric acid. Okay, so perchloric acid is 1, nice and friendly. Sulfuric, nitric, and then our little hydro series. So again, it would be important to memorize these because I will just present them and just hopefully have you know that they are strong acids. What's another important thing that would probably give you a telltale that this is a strong acid? What has to come with a weak acid? Weak acids are governed by equilibrium constants, right? Do I need to determine an equilibrium constant for any of these strong acids? No, because we assume everything goes to product, right? We assume a single-headed error. So if I don't give you an equilibrium constant and you're dealing with an acid, it's a probably good assumption to make that that is going to be a strong acid, okay? Okay, again, what's the point of this? So what if we wanted to find the pH of a strong acid solution? So let's say that we had one of our nice, friendly little strong acids, something like HCl, right? So we put HCl in water, and we want to know what is the overall pH of this solution, right? So let's say I put in, 0.250 molar of HCl. Because, and I drew this incorrectly, because this is a single-headed arrow, what can I assume about how much H3O plus I produce, given that I put in 0.25 molar of HCl? So this is a 1-to-1 relationship. So for every 1 HCl I put in, I get 1 H3O plus. So if I put in 0.25, how many H3O pluses do I get? 0.25, right? So this is in concentration. If I wanted the pH of this solution, what would I then need to do? So for pH, I would then just take the minus logarithm of whatever my H3O plus concentration is, 0.250, and that would give me a pH equal to 0.60, okay? So for strong acids, however much acid you put in, you should assume that that's how much H3O plus gets produced, and just take the minus logarithm of that to get the pH of that solution. Okay, so now that's strong acids. That was easy, right? You just take the minus logarithm of something, you move on. What about finding the pH of a weak acid solution? Is what we're going to be dealing with the majority of the time in here. So let's say I had a weak acid, some unknown weak acid like this HA, right? We put it in solution, and it does this little acid thing. It donates a proton to water. It forms this conjugate base, and it forms H3O+, right? We know this is a weak acid, so we know that this is not a single-headed arrow. However much I put in of this guy, I cannot assume that I make this much of this guy. But what you will also be given is the equilibrium constant for this reaction, right? And that is what this acid ionization constant is the equilibrium constant that governs this acid dissociation, this acid ionization, okay? So let's say I know that. I'm given the equilibrium constant for that. And I also know my initial value of the acid that I put into the solution. How do you think we're going to go about utilizing an equilibrium constant, an initial concentration, to go and figure out our equilibrium concentration of something? Equilibrium constant, initial concentration. We want to find the equilibrium concentration. I wonder how we could do that. I wonder if we've done that ever before, successfully on an exam. I don't know. So the solution to this little problem is what? An ice table, right? This is just another equilibrium problem. Equilibrium constant, we've got initial concentration. If we want equilibrium concentrations, then we need to draw out our little ice table, and we need to solve for x, okay? So let's say that we replace our little unknown HA with this guy, which is a weak acid. Which acid is this? Acetic acid, right? So this is the acid of acetate, the polyatomic ion acetate. This is acetic acid. So we put our little acetic acid in water, and we note that we make an initial concentration of this guy of 0.1 molar, okay? We want to figure out, oh, hey, what's the H3O plus concentration at equilibrium, and then we're going to determine the pH from that. So my first step in this would be to write out my pretty little ice table. So I've got HC2H3O2 plus water goes to make H3O plus our little acetate, C2H3O2 minus. And then on the left-hand side, I'll draw my little I, my little C, my little E. Which values can I just ignore entirely? I don't care about at all. Boring little water here, our pure liquid, doesn't change its concentration, so we just get rid of that. What about my initial values for these guys? Acetic acid, what is the initial concentration of our acetic acid? 0.1, so that was something that was given to us. What can I assume about my two products? 0 and 0. And then how do you think I'm going to represent this change, my little C? Probably as some unknown value x, right? So if we start initially with all reactants, then we're going to lose an x from our reactants, right? We're going to go to form products. And what's really nice about these little Kas, or these acid problems, is that this is always a 1-to-1-to-1 ratio. It will never change, right? So we will lose an x from reactants, we will gain an x, and we will gain an x. That's a 1. It's a times a 1. That's completely reverse of what it was supposed to be. And then for equilibrium, we will sum our columns. So we're left with 1.1 minus x. We're left with x and x. So what do you think is next? Now that we have our equilibrium values in terms of x, and one of our little unknowns, what we actually want, is in there, how do you think we're going to solve for x? So we know the K for this reaction, and we also know the equilibrium constant expression, right? So what I'm going to do is I'm going to take my little equilibrium values, this guy, I could use my pen, right? This guy and this guy and this guy, and I'm going to plug it in to my equilibrium constant expression. I'm going to use the value of the K to determine what this value of x is. Okay, so when I do that, I plug this guy in. I've got x for my H3O plus, I've got x for my acetate over my equilibrium value for my acetic acid. This is all going to be equal to 1.8 times 10 to the minus 5. So if we reduce this, if we did some math, and we tried to make this a little bit more simplified, we would end up with x squared over 0.1 minus x is equal to 1.8 times 10 to the minus 5. What's the problem with this? I want to solve for x. That's my big goal here. What am I left with as it is right now? This is a quadratic equation, right? Or we need to utilize the quadratic formula to solve for x. But what's great about all of these acid ionizations, or all of these weak acids, is what is the value of Ka? Ka is very tiny, really small, right? So all of these are going to follow the exact same format. If Ka is so tiny, what can we assume about taking 0.1 and subtracting x from it? It's essentially not going to change that 0.1. X is going to be really, really, really small. And so because of that, we can ignore it on bottom. We can ignore subtracting it from a big number. Okay? So if we do that, then this simplifies down to x squared over 0.1 is equal to 1.8 times 10 to the minus 5. Is it a little bit easier to solve for x? Yes, right? So I'd multiply 0.1 on both sides. I would take the square root, and that would give me x equal to 1.3 times 10 to the minus 3 molar. So that is x, right? What was the original question? They wanted H3O plus concentration at equilibrium. What else did they want? pH. What does x represent right now? H3O plus concentration at equilibrium, right? So this is our equilibrium concentration of H3O plus. If I wanted the pH, how would I go about getting that? I would just take the minus log of whatever number I just solved for, minus 3, minus log of that, and I don't even think I did it, unfortunately, 1.3 e to the minus 3 logarithm gives me a 2.88. Oh, 89. So weak acids always follow this exact same format, right? If you want to determine the pH of a weak acid solution, you solve an ice table, you solve for x, and you take the minus logarithm of x. Okay? Okay. Is everyone good with that? So I'm going to let you try one. There was another little example, but I figure you guys are really on the ball. So I want you to find the pH of a 0.25 molar hydrofluoric acid solution. So hydrofluoric is HF. Before I let you get started, what else should I include with this? It's a weak acid, I'll tell you that. So I will also need to tell you what the Ka is. That will have to always be provided for things like this. Let's see if I did it. Oh, I did. The Ka for HF is 3.5 times 10 to the minus 4. Okay, so I want you to figure out what is the pH of this 0.25 molar HF solution. Shame. Okay, so let's go ahead and talk about this one. Most of you got this correct. So the pH for the solution is 2.03. That's good. Good job if you did that. Again, we're dealing with HF, this nice little weak acid. It has an acid ionization constant of 3.5 times 10 to the minus fourth. Things that we know about it. We know initial concentration, 0.250. Oh, no, yeah, 0.250. Okay. We know nothing about water. We don't care about water. We know initial concentrations of our two products, right? We know that the change we're going to represent as a minus x, a plus x, and a plus x. And at equilibrium, we have our little 0.25 minus x, x, and x. We know the value of Ka. This is 3.5 times 10 to the minus 4. And we're going to plug in the little concentrations of our products at equilibrium. So we've got an x times an x over the concentration of our reactants. We've got a 0.25 minus x. Do we care about that x? No. This is one of those ones that you may want to check at the end just in case, but for the most part, no, we never care about x because it is insignificant when it's subtracted away from this massive large 0.25, okay? All right, so then how are we going to solve? We're going to multiply both sides by 0.25, and then we're going to take the square root. That should give you an H3O plus concentration equal to 0.00935 molar. And again, that is our little H3O plus at equilibrium. If I want the pH, what should I now do? take the minus logarithm of this number, right? So for the most part, with respect to these types of problems, they're going to skip the whole, hey, what's H3O plus? And they're going to go straight to what's the pH of the solution. Okay, so the pH here is minus log of our number, 3.5, which gives us a pH equal to 0.03. I've been a little fast and loose with my significant figures, but again, probably right here I should have reported 2 sig figs because of this guy. And so then if I report 2 sig figs there, I take the logarithm of that, I should only have 2 places past the decimal point in my result, which is what I have, which is great. Okay, so that is going to be it for tonight. You guys have Okay, so I had skipped a few slides in the lecture that I did last Thursday to kind of get to some of the stuff I wanted to talk about. So at the beginning of this video assignment, I'm going to go back and talk about those slides that I skipped and the topics that are covered therein, and then I'll move forward and finish up with the remainder of what is presented in this section of the slideshow. Okay, so what we've been doing so far, what we kind of ended with respect to our weak acids and pH, is the fact that we could take a Ka of a weak acid, and we could also take the initial concentration of the weak acid, and we could utilize that data to determine the proton concentration at equilibrium as well as the pH of that solution. Okay, so again, given a Ka, an initial concentration of weak acid, we could utilize that to determine the pH of that resulting solution. And so now what we're going to do is kind of the reverse. We're going to say, okay, we don't know what the Ka of an acid is, but what we do know is the initial concentration of it, and we also know the pH of the solution that it produces. So can we utilize those 2 types of data, initial concentration and pH, to determine the Ka of any weak acid that we have. Okay, so number 1, I'm going to go ahead and just draw out, let's say that we have a nice little solution of weak acid, and in this problem it is a 0.1 molar weak acid solution, so it's some sort of unknown, and we measure the pH of it, and the pH is 4.25. So if I draw that in my little beaker, so I've got my little weak acid solution, this is our unknown HA, we know that it is a 0.1 molar solution, and we've got in with our little pH meter after we've made it, and we've measured that the pH is equal to 4.25. So how can we utilize this type of data to determine the Ka for this unknown weak acid? Okay, so I'm going to go ahead and go back to my ice table. So I'm going to go and draw out my acid ionization equilibrium reaction, where I have my weak acid, it donates a proton to H3O+, donates a proton to water to make H3O+, and then its conjugate base. Okay, so this is the conjugate base of my little weak acid over here. And I'm also going to go ahead and draw out my ice table. Okay, so things that I know right now, as usual, is the initial concentration of weak acids. This is 0.100 molar. Again, we don't care about water because it's liquid. And we're going to assume that both of these guys, as is usual, are 0 as well. Okay, so now, the big question is, what does pH correspond to? So pH is minus log of H3O+, and this is a thing that we have measured. But it's important to note that this is the H3O+ concentration at equilibrium. So for this guy right here. So if I know the pH, this is 4.25 is equal to minus log of H3O+ at equilibrium, then I can solve for the concentration of H3O+. So H3O+ is equal to 10 to the minus 4.25, 10 to the minus pH, which gives me a concentration equal to, I should have done this, 4.25 minus 10 to the negative gives me a concentration equal to 5.6 times 10 to the minus 5th. Okay, so the pH, that's what it's telling you. It's telling you H3O+ concentration at equilibrium. So if this is 5.6 times 10 to the -5th, and then we know that whatever happened to this guy had to happen in an equivalent manner to the conjugate base, so it will be 5.6 times 10 to the -5th as well. And then over here, the equilibrium concentration of the weak acid will just be the initial concentration minus this very tiny number. And so when I actually do that, I take my initial concentration, I end up getting an equilibrium concentration equal to something like 0.09994, right? So with respect to significant figures, this essentially is just equivalent to the initial acid concentration. Excuse me. So you can go ahead and plug it in as this number, but long term with respect to the math, you could also plug it in as just initial acid concentration, because again, it's like 4 sig figs down the road. So maybe I shouldn't have said that, but I'll just say, okay, we plugged it in and it's going to be this 0.09994. Okay, so now I have my equilibrium concentrations, and again, Ka is the constant for this equilibrium reaction, right? So this is equal to the concentration of my reactant, my products, H3O plus times A minus, all over HA, and this is all concentrations at equilibrium. So I can go ahead and plug in my values here. This is squared all over this 0.09994, and I end up getting the Ka, which is equal to 3.13 times 10 to the -8th. And that is our Ka. So that's one way that you could determine the Ka of a weak acid solution. You could measure out your known concentration of your weak acid. You could put it in your beaker. You could then take the pH and know that that pH is referring to H3O plus concentration at equilibrium. And then utilizing the stoichiometry, you could figure out all of the other equilibrium concentrations, plug it in to your equilibrium constant, and get your Ka from that. Okay, so this was the question that was posed after this slide that I just went over. So I'm not going to go over the solution to this, but I would say that this will probably be on the quiz. So maybe try to work on this following the example that I just gave. I will probably be asking for the pKa though, for the acid that you determine, because I like to just add in those little tricks. As a reminder, the pKa is just the minus log of Ka. So whatever you guys get for Ka, which you should know how to do, you'll just take the negative log of it for the pKa. Okay, so another topic that I kind of just skipped over was something called percent ionization. So another way that we can measure kind of like an overall acid strength is by determining what fraction of molecules actually ionize comparatively to the fraction of molecules of acid that we put in to the solution initially, right? So this is what we call percent ionization. So again, this is just a measure of the fraction of molecules that ionize, or the concentration of molecules that ionize comparatively to the initial concentration of acid. And since it is a percent, then we just multiply that fraction by 100, okay? So if you think about it, the larger percent ionization, the stronger the acid, right? So the larger the percent ionization, the more molecules will ionize comparatively to the initial concentration of the acid. So stronger the acid, larger percent ionization. And what we usually utilize to denote how many molecules of acids ionize is the H3O plus concentration at equilibrium, right? So the way we usually measure this is we go through an ice table, we determine H3O plus at equilibrium, we divide it by the initial acid concentration, multiply it by 100, and that will give us the percent ionization. Okay, so as an example, we utilize this 0.2 molar nitrous acid. So note here that this is HNO2, which is nitrous acid. Remember that nitric is a strong acid. This is not a strong acid. This is a weak acid because it is nitrous, okay? All right, so just to kind of get an idea of what types of values you should be expecting for this percent ionization, let's say that we go in, we make a 0.2 molar nitrous acid solution, and we go through and we determine at equilibrium there are 9.6 times 10 to the minus 3 H3O pluses, okay? So the percent ionization for this solution would be the 9.63 times 10 to the minus third divided by the initial acid concentration times 100, which gives us 4.8%, okay? So if we went back to our table of weak acids, nitrous acid has a Ka equal to 4.6 times 10 to the minus 4, which is actually comparatively fairly large compared to all the other weak acids. So even though this is a stronger weak acid, we still only get 4.8 molecules out of every 100 molecules that are put in there that actually undergo this ionization, right? So again, 4.8 is approximately 5. This tells you that for every 100 molecules, right, percent, for every 100 molecules, you only get about 5 of them that actually undergo this ionization, which again gives you an indication that the majority of the time, these guys stay together because they like to be with one another. Okay, so one little thing, I'm gonna go ahead and actually do this problem. So I've given you another problem that features this nitrous acid. So now we have increased the concentration to 2.5 molar, and we want to know what the percent ionization is for this solution. So I'm going to do this, and I'm going to try to illustrate something that kind of results out of this that you would maybe not expect, okay? So I've gone ahead and rewritten my problem on my little blank slide here. And so again, the purpose of this right now, we want to determine the percent, the percent ionization of this 2.5 molar solution of nitrous acid, okay? So my first step in this is, number one, I need to know the equilibrium concentration of H3O plus, because we have defined percent ionization as equilibrium concentration of H3O plus divided by initial acid concentration and this is initial, okay, times 100. So we already know this guy, right? This is what was given to us. We had 2.5 molar of this initially. Now we just need to figure out what this guy is to get the percent ionization. And to do that, we're going to go through this exact same thing that we've been doing before, which is we're going to utilize an ice table and the Ka of this acid to determine what this guy is at equilibrium. So same thing, we've got 2.5 molar initial concentration. We've got 0 and 0. Now we're going to subtract x, add x, and add x. And at equilibrium, we have 2.5 minus x, x, and x. So I had already looked up the Ka of nitrous acid, so that Ka was equal to 4.6 times 10 to the minus 4th. So now we can go ahead and use that, plug it in to solve for H3O plus, or solve for x. So take these guys, we've got our Ka is equal to x times x, the concentration of my products, over my reactants, 2.5 minus x. So again, this is a gigantic number comparatively to what x will be, so it would be very smart for us to ignore x on bottom. And when we do that and solve for x, we get an x equal to 0.0339 molar. Okay, and so x is our equilibrium concentration for H3O plus. So now, to determine this percent ionization, we'll go ahead and take this value. We've got 0.0339 divided by initial acid concentration, which is this guy, divided by that guy, so 2.5 times 100. And so the percent ionization for this solution is 1.36%. So fairly simple to calculate for the most part. Okay, so now the only thing is that something kind of seems a little bit off, or it doesn't seem off, but maybe not something that you would expect, right? So if we compared this to that original nitrous acid solution that I had given you, so that original solution had a concentration of 0.2 molar. It had a H3O plus concentration of 9.6 times 10 to the minus 3. But then it had a percent ionization of 4.8%. And again, those are the values that I just given to you in the example of how to determine percent ionization. So now with this solution, same exact acid, but now we have 2.5 molar, so we have increased the concentration. What we see with respect to H3O plus is what you would expect, ideally, an increase in the concentration of H3O plus, right? So we increase the concentration of the acid, we see an increase in the concentration of H3O plus, but what we see is a decrease in the percent ionization. So this is something that I'm not necessarily going to go into the rationale behind why, but it is something that you should kind of have in the back of your mind. So increasing weak acid concentration is going to increase the concentration of H3O plus. That will decrease the pH. But in terms of percent ionization, if we increase the concentration of acid, we're actually going to see less molecules ionize. We're going to see a decrease in percent ionization. So more weak acid, or more concentration of weak acid, less molecules actually ionize. Less percent, let's say that, because that's actually, no, I can't say that. So less percent of molecules ionize. And again, we determine that via this decrease in the percent ionization. Okay, so I may ask you about a percent ionization on the video assignment, but I may be more likely to ask you about just kind of the trend that we see here, where if we increase the concentration of our weak acid, we increase H3O plus, which decreases pH, but we actually see a decrease in the percent ionization. So just maybe that's something that I would consider asking. Those are strong bases. All right, so now what else do you think there are? If there are strong bases, we want to compare it to acids. There are probably also weak bases. Okay, so weak bases are different comparatively to strong bases. So how are weak bases different? So weak bases actually undergo this ionization reaction. So a weak base doesn't have a hydroxide ion associated with it. Instead, it produces hydroxide ions because it acts like a Bronsted-Lowry base. It accepts a proton from water, forming its conjugate acid, and it leaves behind this hydroxide ion. So weak bases form hydroxide because they ionize water. Okay, so this is not a dissociation. This is an ionization reaction. Okay, so weak bases are very similar to weak acids in the fact that the majority of them do not do this reaction at all, right? So the majority of them stay like this in their unionized form. So because of that, we know that the concentration of whatever our base is going to be much greater than the concentration of the hydroxide ions formed. Okay? That wasn't the case with strong bases. With strong bases, those guys were equal to one another. But for weak bases, we know that the majority of it stays like this, and very few of these hydroxide ions are actually made. Okay, so then how are we going to determine the pH of a weak base solution? So it's probably going to be something to do, just like with weak acids, probably going to have something to do with an equilibrium reaction, an ice table, etc. Okay, so how do we quantify this base strength, or how do we quantify how much product exists at equilibrium? So we're going to use a new K, brand new K. This is called the base ionization constant. Okay, so just like we had for Ka, this is Kb, and the little b represents the fact that this is the base ionization reaction, where we have our weak base acting as a base, taking a proton from water, forming its conjugate acid and hydroxide ion. So Kb represents the equilibrium for this reaction, where this little weak base here can be any particular weak base. Okay, so similarly with respect to weak acids, what do you think we can say about Kb's? Do you think they're going to be really small or really big numbers? Really small, right? So for weak bases, the majority of our guys are going to exist as reactants at equilibrium. So very few of these products are going to be formed. And so because of that, Kb's are going to be usually fairly small numbers. And if we zoom in here, we can see a variety of different Kb's for a couple of different weak bases. Okay, so with respect to these small, tiny values for Kb, if I have a larger value, something like 10 to the minus 4th, versus a smaller value, something like 10 to the minus 9th, who's going to be the stronger weak base? Same exact thing with the weak acids. What can we say about Ka versus acid strength? The larger the value of the Ka, what can we say about the acid strength? Stronger the acid, right? So the larger the value of Kb here is going to give us a stronger base. So if we compared 10 to the minus 4th versus 10 to the minus 9th, 10 to the minus 4th is larger. So this Kb gives us the stronger base comparatively. So the larger the value of Kb, the stronger the base. But again, if it has a Kb, it is a weak base. So it's like the stronger the weak base. Okay, so Kb, that's great. Now let's talk about how you guys are going to determine the pH of these basic solutions. So if we had a strong base, determining the pH for these basic solutions is fairly simple, right? If we had something like potassium hydroxide, so potassium hydroxide is a strong base. It completely dissociates into K plus and OH minus. Let's say I had a solution of 0.225 molar KOH. What would be my concentration of hydroxide ion in this solution? So just for KOH, it's just 1 to 1. So if I have one of this guy, I've got one of this guy. So for KOH, if I have 0.225 molar, I will also have 0.225 molar of OH minus. So if I know that about the OH minus, how would I get the pH of the solution? So if I know OH minus, if I want the P, right, if I want a pH, pH is minus log of what? H3O plus, right? Do I have H3O plus for this solution? No, right? I have OH minus. Is there a relationship, though, between OH minus and H3O plus? Kw, right? So that's one way that we could go about this. We could say Kw is equal to H3O plus times OH minus. If we know OH minus, we could substitute that in. We know that Kw is 1 times 10 to the minus 14th. So we could solve for H3O plus. And then what would we do if we wanted the pH? Take the negative logarithm of that. Okay? So another way, which is the way that I prefer to go about doing this, is another relationship that we derived last time was the fact that 14 is equal to pH plus POH. Okay, what was POH? POH was just minus log of OH minus. Do I have OH minus? Yes, right? So I could plug this guy in here and determine that my POH is equal to 0.65. And then how would I get pH? Coming back up to this relationship. So 14 is equal to pH plus POH. So pH is equal to 14 minus POH. which gives us a pH equal to 13.35. That's not what I want. This guy. And 5. So that was the pOH, right? So I plugged in minus log of my OH minus concentration, which was this guy that we got from the concentration of KOH, 225. When I did that, that gave me a value of 0.65.
Okay, then why is pOH on there 0.64? So is it a typo?
Yeah, sorry, it's rounded wrong. My bad. Okay, so strong bases. How would you determine the pH? Same exact thing if you had something that had 2 OH minuses, only you would need to include the stoichiometry of the reaction, right? So for strontium hydroxide, how many OH minuses will I get for every strontium hydroxide? 2, right? So if I had a 0.0015 molar strontium hydroxide solution, what would be my concentration of OH minus there? 0.003. And so then pOH of that guy would be minus log of that number, which gives me a value of 2.24, I believe. Let me check. 2.52. And then pH from that, again, would be 14 minus pOH, which would give me a value of 11.48. Strongly basic solutions, okay? Fairly simple. Just be concerned with the stoichiometry and make sure to take note of that.
So 0.0015 is multiplied by 2 because of the substrate?
Yeah, because when we look at the dissociation of strontium hydroxide, when this guy breaks up, it's going to form 1 strontium ion, but then it's going to form 2 hydroxide ions. So for every one of these, you produce 2 OH minuses. Okay, so now what about a weak base solution? So let's say that we want to determine the OH minus concentration as well as the pH of a 0.33 methylamine solution. So number one thing I'm going to do in this problem is I'm going to look up what the Kb of methylamine is. So this usually comes back to some sort of chart. When I look at the Kb of methylamine, methylamine is given by CH3NH2, and note this nice little lone pair of electrons. The Kb for this is equal to 4.4 times 10 to the minus 4 Kb. Okay, so again, Kb deals with this guy acting like a base. So we have our methylamine, it's in water, and it's going to ionize water. It's going to take a proton from water. It's going to form its conjugate acid, so CH3NH3+, right? Just putting a proton on our little weak base, and it's going to leave behind OH minus from the water. It's taking a proton from water, so all that's left over is OH minus. And again, this is what this equilibrium constant represents. It's the equilibrium constant for this reaction. So now to determine the OH minus as well as the pH for this solution, I'm going to draw my little ice chart. I have my initial concentration of methylamine. This is 0.33 molar. I'm going to ignore water, and I'm going to ignore or say 0 and 0 for the initial concentration of my two products, okay? So I'm going to go through this like I normally do. I'm going to subtract from my reactants. I'm going to add to my two products. And to determine the equilibrium concentrations, I'm just going to sum my columns. Okay, so now I'm going to substitute this in for the Kb expression. So Kb is equal to the concentration of our conjugate acid times the concentration of OH minus at equilibrium all over the concentration of our weak base. And again, this is coming just from the equilibrium constant expression for this reaction. So I'll go ahead and plug in my values. I have a value for Kb, it's 4.4 times 10 to the minus fourth. My values for my two products at equilibrium are X and X. And then the value for my one reactant is 0.33 minus X. Okay, so what would be a safe and fair approximation to make given my overall magnitude for Kb in this problem? I'm going to ignore the X on bottom. So I'm going to ignore this guy and essentially just going to act like it goes away. So then, makes the problem a lot easier in solving for X. I'm going to multiply both sides by 0.33 times 0.33. And then I'm going to take the square root of that. Let me do that. 4.4 e to the minus 4 times 0.33 gives me 1.45 times 10 to the minus 3 equal to x squared. When I take the square root to solve for x, I end up with a concentration, or an x, equal to 0.0120 molar. So I'll make sure on that one. Nope, that was not it at all. Did I do that right? 4.4 e to the minus 4 times 0.33. Take the square root. Missed the 0. That's a big important one to note. So yes, this is correct, what I've written down. Okay. X is equal to 0.0120. So the big thing to note about this is I want the pH of the solution, right? But what have I just solved for? What does X represent if we go back to our ice table? It represents OH minus, right? And so again, how do I get pH from OH minus? My preferred route is to find POH. So POH is minus log of our OH minus. POH for this solution is equal to 1.92. And then how would I get pH from that? 1.92 gives me a pH equal to 12.08. Okay, so let's try that on our own. I'm going to put up a Socrative question. So for this one, I want you guys to determine the pH and the OH minus of a 0.1 molar ammonia solution, and I will look up the Kb of ammonia shortly. Ammonia. I should remember that. Okay, so go ahead and get your answer in, most you have, so we can just stop that. Yep. One, so we'll let it open. All right, so most of you guys have got this right, given a few issues with significant figures. So the pH of this solution ends up being 11.13. And again, we go about doing that using this nice little ice table that I've already drawn, given the fact that ammonia is this beautiful little weak base. So it loves to take protons from water. In the process, it generates this little conjugate acid, and it leaves behind hydroxide from the water. Okay, so when we start this, we always start with our initial concentrations, and we represent the change as this unknown variable x, and x. So at equilibrium, we are left the same thing as we are always left with. Okay, we'll plug that into our equilibrium constant expression because we know what Kb is for this weak base. So this is x squared over 0.1. Again, we will ignore that x on bottom because it's going to be very, very, very tiny. When we solve for x, we get an x equal to a 0.00134, which again represents OH minus. That is our pretty little x that we have solved for. So to get pH from that, I will first take the POH, which is minus log of what we just solved for. This gives me a POH of 2.87. And then for pH, I'll just take 14 minus what I just solved for POH. And that pH ends up being, again, the 11.13 with respect to 2 sig figs, past the decimal. Okay, so everyone's bored with this. You've got it down. Super easy. Don't even need to discuss it anymore. So, given that we have just introduced you to weak bases, we are now going to move into the acidic and basic properties of salt. Okay? So first off, what is a salt? I kind of just use this word salt, just freely use it. I assume everyone knows what I mean by that. But what is kind of like the definition of a salt? What type of compound are salts? Ionic compounds. Okay, so anytime I'm referring to a salt, all I'm saying is that we're dealing with an ionic compound. Okay, and remember that salts, when you put them in water, tend to dissociate. What does that mean? So if it's an ionic compound, something like NaCl, you put it in water, what happens? Did it stay together as NaCl? No. So it breaks apart into little component ions, and they float around in solution, producing a nice little electrolytic solution. Okay? All right, so now, given that is what a salt is, I want us to consider this little guy, right? So HCO3, 1-, this is a polyatomic ion. What type of polyatomic ion? What do we call this polyatomic ion? Has something to do with carbonate, right? Because CO3, 2- is carbonate. If there's an H in front of it, though, what do we call that? Bicarbonate, right? So this we just refer to in kind of a canonical version as bicarbonate. Okay, so note that if you were to take bicarbonate ion, and you were to put it in water, it would react like a Bronsted-Lowry base, so it would take a proton from water, forming its conjugate acid, which is carbonic acid, as well as hydroxide ion, okay? That's what would happen. You put bicarbonate in water. Have you ever seen bicarbonate just by itself, though? Can you go to the store and buy a box of bicarbonate ion? So bicarbonate, yes, we call it bicarb. That's kind of a misnomer again. But is it just going to come like this negative charge ion around a bunch of different other negative charge ions? No, it's always going to be balanced with some sort of counter ion. And that tends to be things like sodium or potassium, etc., right? So usually the way we're going to get bicarbonate into solution is, again, in the form of this salt, something like sodium bicarbonate, potassium bicarbonate. When we put it in solution, though, it again is going to dissociate. It's going to break apart into its sodium ions and its carbonate ions. And we know that this bicarbonate acts like a what? A Bronsted-Lowry base, right? So that means that if you put sodium bicarbonate into water, it would produce this bicarbonate ion, which would act like a weak Bronsted-Lowry base. What do you think that's going to do to the pH of the solution? It's going to be greater than 7 or less than 7. If it's going to be weakly basic. Greater than 7, okay? So this is a salt that when you dissolve it in water, changes the pH of the solution from what you would expect for just water. What would we expect for just water? 7, right? It's going to change it, make it slightly basic, so it's going to be just a little bit above 7, okay? All right, so what is this? This is the negative charge part of the salt. What do we call that? This is an anion, right? So anions are the negative charge particles, or negative charge ions with respect to salts. What are the positive ones? Cations, okay? So this is an anion that when we put it in water, behaved as a base. So what does that mean long term with respect to salts? So potentially, all anions could be slightly basic, or could behave like a base, okay? We could think about it in the fact that all anions are essentially just the conjugate base of an acid, okay? So for example, let's imagine that we had some sort of acid like HX, okay? Let's imagine that that acid is fairly strong. So we have this nice little strong acid. When we put this guy, move this over. When we put this guy into solution, our HX, we put it into water, it forms again H3O plus this X minus, right? So this guy, or all anions, could potentially be the conjugate bases of an acid, okay? Now, how do we know whether or not this conjugate base is going to act like a base or not? So it's going to come back to the fact, or the difference between a weak acid versus a strong acid, okay? So I want to erase this because I don't like the way I've drawn it. So this guy, getting rid of, is a strong acid. Okay, so strong acids completely dissociate. What does that tell us about the affinity of hydrogen for this other molecule X? If we put this in water, what happens to it? Does it stay together or does it completely break apart? Completely breaks apart because, again, this is a strong acid. So we know that when we put it in water, these guys are going to completely go their separate ways. The H is going to go to the water, and we're just going to have our little H, or our little X minus floating around in solution. So what does that tell you about the affinity of X minus for H? Do you think it likes to be with H? Or do you think it's like, hey, I'm cool on my own, peace? Because when we had it with H, where did it go? Alone, right? So this guy, which is the conjugate base of a strong acid, doesn't have any affinity for hydrogen, right? It has no basicity whatsoever, so we call this a negligible base. So the conjugate bases of strong acids have no basic tendencies because, again, they have no affinity for protons, and so they will be what we call negligible with respect to basicity, okay? All right, so now let's imagine, instead, we have a weak acid. So a weak acid will represent as this HA. Again, when we put it in water, part of it ionizes to form H3O+, as well as its conjugate base, okay? Now, what's the difference between this weak acid and the strong acid? When we put it in water, what happens the majority of the time? Do they go apart, they go their separate ways, or do they stay together? They stay together. These guys like to be together, right? The majority of the time, they stay together. They don't actually go and ionize and give up the proton for water. So what do you think that tells you about the affinity of this conjugate base for protons? If they like to be together, do you not think that this H- will go out and take a proton from water if it has the opportunity? Yes, it will. Okay, so again, this is the conjugate base of a weak acid. And because this A- actually really likes to be with protons, because again, there was a strong affinity for them in the acidic form, then this guy will act like a weak base. If you put it in water, it's going to go out, it'll take a proton from water because, again, it likes to be with its hydrogen in the first place. Okay? So the conjugate base of a weak acid produces a weak base. So how do we know whether or not a salt, or the anion of a salt, is going to produce a basic solution? If I looked at something like chloride ion, I knew this was floating around in water in the form of something like sodium chloride. What acid would chloride have derived from? HCl, right? How would you know? You'd put an H in front of it, okay? Is HCl a strong or a weak acid? Strong acid. So what does that tell you about the basicity, or the basic behavior of chloride? It is the conjugate base of a strong acid, so does it have any affinity for protons whatsoever? No, right? It does not, right? So anything, an anion that is the conjugate base of a strong acid, doesn't do anything with respect to basicity, so what can you assume that the pH of the solution is there for, if they're all floating around in water? 7, right? The only thing that's affecting the pH of the solution is water itself. So if you have an anion that is the conjugate base of a strong acid, the pH is essentially just going to be 7 because, again, this doesn't behave like a base at all. On the other hand, if we have an anion that is the conjugate base of a weak acid, something like fluoride, again, this derives from HF, which is a weak acid, and we know that F-, because it came from a weak acid, has a slight affinity to take protons towards itself, because it likes to be with proton. Because of this guy is going to behave like a weak conjugate base, and it's going to make the solution slightly basic. So the pH of these types of solutions is going to be a little bit greater than 7 usually. All right, so again, big overriding question. You have a salt. How do you know if it's going to change the pH? You look at the anion, and what do you think to yourself? You say, what type of acid would this anion have derived from? If it's strong, it's not going to do anything. If it's weak, it's going to make the solution weakly basic. Okay, all right, so that's great. Unfortunately, we can't just leave it as talking points and moving on. We actually have to do some sort of quantitative measurement on all of this. So, long term, what we're going to want to be able to do is calculate the pH given that we have a salt that is going to affect the pH, okay? So we put a salt in solution, we want to be able to calculate its pH. Unfortunately, though, what's going to happen, so let's say, for example, we put sodium fluoride into solution as a salt. We know now that fluoride ions are weak bases, right? Because again, this is the conjugate base of a weak acid. To calculate how basic the solution is going to be, to calculate the pH of the solution, we would need the Kb for fluoride. Unfortunately, though, you're not going to find that in a table. Okay? Instead, what you will find is the Ka of its conjugate acid. What is the conjugate acid of fluoride ion? HF, right? So if you looked up in the table, you would find the Ka of HF. If you looked in the table for a Kb of F minus, you would not find that, okay? There is a relationship for the two of them, though. So if we have one, we have the Ka for a weak acid, we can derive the Kb for its conjugate base. So how are we going to do that? So this all goes back to Kw, okay? Everything always goes back to Kw. So again, just as a reminder, Ka is the equilibrium constant for the weak acid. Okay? Kb is the equilibrium constant for the conjugate base. Okay? If we take these two reactions, our two Kas and our Kb, and we multiply them together, something amazing is going to occur. So I'm going to take Ka, again, equilibrium expression for the weak acid, and I'm going to multiply it by Kb, which is the equilibrium expression for the weak conjugate base. What amazing thing is going to occur? So we've got our Ka here. Ka times Kb is equal to, so now I'm going to substitute in the expressions, right? So for Ka, I've got A minus times H3O plus all over HA, and I'm multiplying that by Kb. So Kb, the equilibrium constant expression, is HA times OH minus all over A minus. Ka, Kb. So notice a few things are going to cancel. It's going to be magic, right? What cancels? We're going to get rid of the A minus, right? Those go away. And we're going to get rid of the HAs. Those go away. What are we left with? Ka times Kb is equal to H3O plus times OH minus. Have we ever seen this before? What is this? What is H3O plus times OH minus? It's Kw, right? So Kw. So Ka times Kb is equal to Kw. Kw is a constant. At 25 degrees Celsius, this is 10 to the minus 14th. So if we know the Ka of the weak acid, given this little expression, we can calculate the Kb of its conjugate base. Okay, all right. So that's where I'm going to end it, because that's what you need to know with respect to the activity. Okay, so now I'm going to skip ahead to kind of cover what I was talking about at the end of class on Thursday. So at the end of class on Thursday, I started talking about anions that are present in salt. Okay, so salts have a cation, the positive charge, and anion, the negative charge. They could potentially be basic, depending on what type of acid they came from, right? And so at the end of class, I'd made this case, well, the anions that were the conjugate base of a strong acid were what we call negligible with respect to basicity, right? So they did not act like bases at all. This would be something like chloride ion or bromide ion. These are all the conjugate bases of strong acids. And so again, they don't like to be with hydrogen. They don't want to be with hydrogen. They are not going to act like a base and take a hydrogen from anything else, okay? On the other hand, if we had conjugate bases or anions that were the conjugate bases of weak acids, then these guys would themselves be weakly basic. So weakly basic, again, conjugate bases of weak acids. These would be things like fluoride ion or acetate ion. right? Because again, these are both the conjugate bases of weak acids. What does that tell you? What does a weak acid tell you about the affinity that these guys may have for hydrogen? Weak acids like to stay together, right? So for the most part, fluoride and acetate, they like to be with hydrogen. And so they will have a tendency to go and take a hydrogen, act like a base from things like water, okay? All right, so again, these guys, these anions, aren't just going to come by themselves. Instead, if we're putting them into solution, they're usually going to come in the form of some sort of ionic compound, some sort of salt, right? So these guys would usually be found in the form of sodium fluoride or potassium acetate or something like that, right? So these guys, these are fully soluble salts. Whenever you put them in solution, they're going to dissociate, and we're going to get our fluoride or acetate floating around, which is going to make the solution weakly basic. Okay, so now we're going to take that, and we're not only just going to say, oh yeah, I think this solution is going to be weakly basic, but we're actually going to calculate the pH for these various salt solutions. Okay, so as an example, I have a solution of 0.1 molar sodium formate. Okay, so this guy here is sodium formate. It's a salt, right? And it contains, as an anion, this guy, the conjugate base of a weak acid. This weak acid is formic acid, HCH2O. Okay, so this, again, is a weak acid. And formate is a conjugate base of this weak acid. So now the question is, well, how do we calculate the pH of this solution knowing that formate is going to produce a weakly basic solution? Oh, and let's note that was not the correct chemical equation for this weak acid. Formic acid is HCH2O, pardon me. Okay, so how am I going to go about this? So there's a couple different parts to this problem, and that's kind of the issue with utilizing these salt type problems with respect to pHs. There's a lot of little moving parts that go into this, okay? So number one, first thing we have to recognize is the fact that we're putting something like sodium formate into water, okay? So we have this guy, NaHCO2, right? And let's say it's a solid salt, okay? And we know it's fully soluble, so that when we put it into water, it dissociates into Na+, and they're going to be floating around, and then these formate ions, CHO2-. And again, they're going to be floating around. So this is the first step in understanding this. This is the dissociation reaction that essentially is how we get our formate into solution, okay? What we know is how much there is of this. So we know that we've made a 0.1 molar sodium formate solution, and because this is fully soluble, that means that for every one of these that we have put into solution, we're going to get one sodium as well as one formate. So that's a big assumption that we can make, right? That because this guy is super soluble, it will dissociate completely into its two component ions, sodium ion and then formate ion. And so now that is how we determine what concentration we're going to be dealing with respect to our weakly basic anion, okay? All right, so now we know what concentration we have of our little anion. Now we're going to see what happens to it now that it's by itself, it's dissociated from its sodium when it's in water, okay? So now we're going to write a second equation where we take our formate, it's floating around in water, and we know that because it is the conjugate base of a weak acid, right? When we put it in water and it's just by itself, it is going to act like a base, weakly basic. And so in doing that, it is going to be a base. It's going to take a proton from water to form its conjugate acid, and it's going to leave behind hydroxide ions from the water. Okay, so again, this is what we call this base ionization reaction, and this is what Kb as an equilibrium constant is referring to. You have a base, it takes a proton from water, forming its conjugate acid and hydroxide ions. All right, so now if we want to figure out how much OH minus is present at equilibrium, we're going to need to treat this like another equilibrium problem, right? So we're going to have an I, a C, and an E. And now the big thing is we know what our initial concentration is of our formate. This was from the salt. It was 0.1 molar. We're going to ignore the contribution from water, or the fact that water is there at all. And then we're going to go ahead and solve this like we've been solving all of these guys. Plus x, minus x, x, and x. Okay? All right, so now we have our concentrations for everything at equilibrium in terms of x. The only thing that we really need to know now is the Kb for this problem. Unfortunately, and this is why I made that big case at the end about Ka and Kb and Kw, is the fact that if you were to go into a book and try to look up the Kb for an anion like this by itself, you wouldn't find it, right? Instead, what you would find is the Ka for its conjugate acid, HO2 formic acid, right? And so when you do that, you'd look it up in your book, and you would find a Ka for formic acid equal to 1.8 times 10 to the minus 4th. And so now we also have a relationship that relates the Kb of the conjugate base to Ka of the weak acid, and that is Kw is equal to Kb times Ka. We know Kw, we know Ka, so now we're going to solve for Kb. So Kb is equal to 1 times 10 to the minus 14th, Kw divided by the Ka times 10 to the minus 4th. This gives us a Kb equal to 5.6 times 10 to the minus 11th. And now we are ready to solve for OH minus, or X, at equilibrium. So I'm going to go ahead and take my Kb, 5.6 times 10 to the minus 11th is equal to X, all over 0.100 minus X. And again, it would be smart to ignore this on bottom. So when we ignore that and solve for x, I end up getting an x equal to 2.36 times 10 to the minus 6 molar. And again, this guy is OH minus. The original problem asked for the pH of this solution. So I'm going to take this, my OH minus concentration, and I'm going to determine the pOH by taking the minus log of this. That gives me a pOH equal to 5.63. And then I'm going to get the pH by just going back to my relationship 14 is equal to pH plus pOH. So pH is equal to 14 minus pOH, which for this problem gives me a pH equal to 8.37. So lots of little different moving parts to this. Again, note that the pH here is greater than 7, so that tells you that, yes, it is a basic solution. It's weakly basic though, right? So it's like at an 8.37, as opposed to something like a strong base would be at 10 to 11 to 12. So this is a weakly basic solution. Again, many different parts. The big assumption that you should always make is that whatever the concentration is of the salt that you put in is going to be the concentration of the anion that's going to act like a base. Again, you'll have to go and find the Kb from the Ka of the conjugate acid, and then when you solve for X, you should realize that you're solving for OH minus. If we want pH, then you have to transfer OH minus into H plus, and then pH from that. All right, so for the video assignment quiz, I'm likely going to ask about this one. So this is a different salt solution. It is sodium acetate. So acetate, C2H3O2 minus, is the conjugate base of acetic acid. So you may want to look up the Ka of acetic acid because, again, you're not going to find the Kb of acetate. And then, same type of problem. You have a salt solution. I want to know what the pH of this is, going through it just like I did in the previous example. So this will probably, as is, written directly as is on the video assignment quiz. Okay, so we've just been looking the last few slides at the various acidic and basic properties of anions in salts, right? So as a reminder, we have a salt. There is an anion, which is the negative charge part of the salt, and we have cations, which are the positive charge molecule in a salt, okay? And so we've looked at the acidic and basic properties of anions and whether or not we could predict whether an anion is going to produce a basic solution or whether it is going to be a neutral solution. And so now we're going to do the exact same thing with cations, because depending on the cation, depends on whether or not we're going to get any type of modulation in pH as a result of it, okay? So with respect to cations, we can categorize our cations in 3 separate categories. So the first one is the boring one. These are going to be cations that are just counter ions for strong bases. The second one are going to be cations that are the conjugate acids of weak bases. And then the third one are going to be cations that are small, highly charged metals, okay? So again, depending on the cation that we are utilizing is going to depend on how it affects the pH of the solution. So the first one that we start with is this boring one, which are cations of strong bases, or counter ions of strong bases. And in general, these guys are our group 1 metals, our group 2 metals, group 2 metals, and then all other metals that are kind of just okay with respect to charge, right? So most metals, and we'll show just one example of kind of an exception to this at the end, most metals kind of fall in this category, okay? So again, what we categorize them as in this manner is we say, oh, they're the counter ions of strong bases, and so sodium tends to be the counter ion of our strong base, sodium hydroxide, potassium, etc. So big idea behind this is that these guys do not affect the pH at all, right? So again, this is going to be things like sodium, potassium, calcium, magnesium. These guys, when we put them in water, will have no effect on the pH. And so if they're present in water in the form of a salt, then the resulting solution is just going to be pH neutral, right? It's just going to be the pH of the background water, which is pH of neutral. Okay, so if you're looking at a cation, it's a group 1 or group 2 metal, or it's pretty much any type of metal that isn't very highly charged, then we know that they're not going to actually affect the pH at all. They are pH neutral. Okay, so then the second category is going to be a little bit different, and this is very comparable for what we saw for our anions, okay? So the second category are going to be cations that are derived from weak bases. So what do I mean by that? So let's imagine a weak base, something like ammonia, right? So ammonia is a weak base. When you put it in water, it'll go and take a proton from water, making its conjugate acid ammonium and OH minus as a result. Okay, so this ammonium is the type of cation that this group is referring to, right? It is a positive charge molecule, and it is the conjugate acid of a weak base, okay? So because of that, these types of cations, which are conjugate acids of weak bases, are going to produce a weakly acidic solution because, again, they come from a weak base. They themselves are a weak acid, okay? All right, so these tend to be some sort of like protonated nitrogen. So if you look at a bunch of the weak bases, you'll frequently find nitrogen as an integral part of that. And so if you're ever dealing with some sort of protonated nitrogen molecule as a cation, then that's a pretty big indicator that this is this class of cation, where these guys are the conjugate acids of weak bases. And so because of that, they will make the solution acidic. And if you ever needed to calculate the pH of a solution like this, you would do it very similar to the way we did it for the anions, right? So for the anions, again, this would be a solution like ammonium let's say ammonium chloride. So this is a salt. Again, if you put ammonium chloride into water, it would dissociate into its cation, NH4 plus chloride. We know that this guy isn't going to do anything, but this guy is going to make it weakly acidic. And if we wanted to actually calculate the pH that resulted from the solution, then we could do that as long as we knew the concentration of our salt, and therefore the concentration of our cation, as well as the Ka of our cation, right? And so again, the Ka for ammonium would probably come from the fact that you can look up the Kb of its conjugate base, right? The Kb of NH3, and the fact that Ka times Kb is equal to Kw. Okay, so a very similar type of problem that we see with respect to how we calculate the pH with our anions that are weakly basic. Okay, so again, this is the second category of cations, right? So if you did have a cation that you thought derived from a weak base, it would be a weak acid itself, and so it would make the solution weakly acidic. And so then the last little category with respect to these cations and how they affect the pH was this small, highly charged metals, okay? So all I'm gonna say about this is that if you have a small, highly charged metal as your cation, it will also make the solution weakly acidic. Now, I'm not gonna necessarily go into why that is the case, but just note small, highly charged metals make the solution weakly acidic. So what do I mean by small, highly charged metals? So small usually means things like aluminum, as well as the first row of transition metals. So if we move beyond the first row of the transition metals, we tend to be too big at that point in time. So small means aluminum or the first row of the transition metals. Highly charged means it needs to have at least a +3, a 3+ as its overall charge. 2+, 1+, those are not highly charged. 3+ though is a highly charged metal. Okay, so small highly charged metals would be things like aluminum 3+, things like iron 3+, or copper or cobalt 3+, etc. Okay, so any type of metal in that first row of the transition series that has a 3+ charge would categorize in this little category, and again, they would make a weakly acidic solution. Okay, so this would be a nice example of a question that you could possibly see, whether it be on a quiz or on an exam, etc. So I've given you guys a list of cations, and I want you to tell me, are they going to produce a weakly acidic solution, or are they going to produce a pH neutral solution? So again, you'd be looking at the cation and kind of determining where it derived from to know whether or not it would be a weak acid or it would be pH neutral. So go ahead, pause this one, and think about it, try to figure out the answer, and then push play again, and I'll go over the answers to these guys. Okay, so hopefully you guys have taken a moment with these ones. So our first one, we've got a nice little cation here. So we've got C5H5NH+. And so again, I tried to say earlier that the presence of nitrogen or a protonated nitrogen is usually a big indicator that this is the conjugate acid of a weak base. So the weak base that this cation derives from is pyridine, which is C5H5N, right? So when we put pyridine into water, it acts like a base, forming C5H5NH plus NOH minus. So this is our weak base. And then this is the conjugate acid of this weak base, right? So this is what we have. This is what we are dealing with. Because this is the conjugate acid of a weak base, it itself is going to be weakly acidic. And so it will produce a weak acid solution, okay? And again, if we actually wanted to quantify that, we could find the Kb for this pyridine, and we could determine the Ka for its conjugate acid from that and calculate the pH that results via some sort of nice little ice table. So this one is acidic. B, so B, we're dealing with calcium 2+. So this was what we would consider a pH neutral cation. And the reason for that is because calcium 2+ is usually just going to be found as the counter ion to a strong base, right? So I said anything like group 1 and group 2 metals tend to just be counter ions. They don't actually do anything with respect to water. They don't donate protons to water, etc. And so because of that, this is pH neutral. And so then number 3, or C, we've got chromium 3+. So again, this is another metal, chromium 3+, but the type of metal this is, it was what would be considered small and highly charged. The highly charged comes from the 3+, right? I said it needs to be 3+ if it's going to be highly charged. And chromium is in that first row of the transition series, and so it would be also considered small. So small, highly charged metals make weakly acidic solutions. And again, I didn't go into the rationale behind that, and I'm not going to, but just note chromium 3+, iron 3+, all of those guys, if they are present, will produce weak acid solutions. Okay, so we have A, weak acid, B, pH neutral, and then C, chromium 3+, which is also a weak acid solution. Okay, so now we've gone through how we can categorize cations, determine whether or not they are acidic or not. We've also gone through how we can categorize anions and determine whether or not they are basic or not. So now we're going to kind of pull all of that together and combine our salts and determine if a salt is acidic, basic, or neutral, depending on the cation and anion that are present in it. Okay, so we're going to define salts into 4 separate categories, again, depending on what it's made up of. And the first category that we're going to define our salts by are going to be salts that have an anion that is pH neutral, as well as a cation that is pH neutral. Okay, so the cation is going to be, again, the counter ion of a strong base. It's going to be things like sodium and potassium, all these really boring little cations. And the anion is going to be the conjugate base of a strong acid. So again, these are going to be things like chloride, bromide, etc. Okay, when we put these guys together and forming a salt, we are going to just get the pH of the background solution, which is a pH of water, which should be neutral. Okay, so this category, you have an anion, doesn't do anything. A cation doesn't do anything. The pH is just the pH of water, which is neutral. All right, so then in the second category, what we're going to be dealing with are cations that do not act like an acid. So we have cations that don't act like an acid, but we have an anion that acts like a weak base. Okay, so this is again going to be cations that are the counter ion of strong bases, our potassiums, our calciums, our sodiums, so these boring little metal ions. But now the anion is going to be the conjugate base of a weak acid. So this is going to be things like our fluoride, like our nitrite, like our acetate. So if we have our anions that are weakly basic, our cations that don't do anything with respect to the solution, then we're going to get a basic solution. So these guys form slightly basic solutions. Okay, so pH neutral, both of the bits of the salt don't do anything to the pH. Now we have pH that are basic because the anion acts like a base, whereas the cation doesn't do anything. The third category should be kind of obvious. Okay, so in the third category, we're going to kind of reverse this. So the third category are going to be salts that produce acidic solutions, and this is because the cation is either the weak acid or the conjugate acid of a weak base, or it's a small highly charged metal. And then the anion is pH negligible, or essentially negligible basicity. These are got to be the guys that derive from strong acids. Okay, so what do I mean by that again? So for this one, we have two different ways that a cation can produce an acidic solution. We have either a cation that is the conjugate acid of a weak base, or small highly charged metals, okay? And then in this solution, the anion is going to be the conjugate base of a strong acid. So this would be something like NH4 for our cation paired with something like Cl-, which again is negligible with respect to basicity, okay? So small highly charged metals or conjugate acids of weak bases paired with these anions that don't do anything with respect to pH of the solution. So this guy is going to form an acidic, a weakly acidic solution. And then the last category, which is, kind of the more difficult one, is what happens when you have a salt that has an anion that will change the pH of the solution, paired with a cation that will also change the pH of a solution. Okay, so again, what are these categories? The cation is either the conjugate acid of a weak base or a small highly charged metal, and the anion is also the conjugate base of a weak acid. So now you have kind of like this battle of the cation trying to make the solution acidic, the anion trying to make the solution basic, and to determine who will dominate, you will have to compare the Ka of the cation to the Kb of the anion. Whoever is larger is going to essentially dominate the overall pH of the solution, okay? All right, so let's actually do some of these, because just reading it off doesn't really make that much sense, but when we're actually putting these into practice, it may make a little bit more sense. Okay, so for example, I have a list of a variety of different salts here, and I want to know if these solutions are acidic, basic, or neutral. Okay, so I have for A, I've got strontium chloride. So when I look at strontium chloride, I first look at, or let's imagine that it dissociates. Okay, so strontium chloride is going to dissociate into strontium 2 plus 2 Cl-. Okay, and so now I can look at my two components. So for strontium is a group 2 metal. It is not highly charged, right? It's just a 2+ charge. And so group 2 metals have no effect on pH. They're not going to act like any type of acids. I also look at my anion here, chloride. So chloride is the conjugate base of a strong acid, HCl. And so because of that, I know that chloride is not going to act as a base. Okay, so it's negligible with respect to basicity because, again, it is the conjugate base of a strong acid, making a negligible base. Okay, so if I have a cation that has no effect on pH, I have an anion which has no effect on pH, then the pH of this solution that we're dealing with is just neutral. It's just the background water. Okay, so then that's A. Let's think about B really quick. So we've got aluminum bromide. So if I take my aluminum bromide, again, this is my salt, and I'm making a solution with it, I'm going to have aluminum ions floating around, as well as my bromide ions floating around. If I look at my cation, this is going to be what I would consider a small, highly charged metal. And so because this is a small, highly charged metal, this is going to produce an acidic solution. All right, so now my small, highly charged metal is paired with bromide. Bromide is, again, the conjugate base of HBr. So this is a strong acid. This is its conjugate base. So because of this, this is negligible with respect to basicity, so not basic. So we have a cation that gives us an acidic solution, an anion that doesn't affect the pH of the solution, it's not basic at all, so this would overall turn into an acidic solution because the cation is what wins here, our small, highly charged metal. Okay, so go with C. So C, we have a little bit different of a salt. We've got CH3NH3NO3. So again, this is a salt. It's kind of hard to see the two different components, the cation and the anion. NO3, though, we know is a NO3 minus charge. So the cation has to be this thing that's apart from that. So this is CH3NH3 plus. So this guy, NO3 minus, this is the, so NO3 minus is the conjugate base of HNO3. So this is a strong acid again. We have another conjugate base of a strong acid. So negligible will not produce a basic solution. On the other hand, we've got this guy who's a little bit different. So CH3NH3 plus. This is the conjugate acid, so conjugate acid of methylamine. So this would have derived from CH3NH2 like this, okay? So this is our weak base. This is the conjugate acid of that weak base. So because of that, this is weakly acidic. And since a weakly acidic cation is paired with a negligible anion, we're also going to get an acidic solution for this guy. So this is neutral, this is acidic, and this is acidic. Okay, so then for D is like the only one that we're going to see that is slightly basic. So for D, we're going to take this guy over here. We've got NaCHO2, so this is sodium formate, which we've seen before. So when this dissociates, we're going to get Na as our cation, and then CHO2 minus as our anion. This is a group 1 metal, so this is not going to have any effect, so no effect on pH. This guy, though, is the conjugate base of formic acid, HCHO2, which is a weak acid, okay? So since this is the conjugate base of a weak acid, it is going to be weakly basic. So we have a cation that has no effect on pH, an anion that is weakly basic. So overall for D, this will also be basic because of the anion. And then the last one is the last category of salts that I talked about. So this one may take a little bit. So we've got as our salt NH4F, okay? So this, when we put it in solution, it's a nice little solid. We put it in solution, we're going to get NH4 plus as our cation plus F minus as our anion, okay? So now, both of these are going to be derived from weak acids and weak bases. NH4 is the conjugate acid of NH3, which is a weak base. And fluoride is the conjugate base of hydrofluoric acid, which is a weak acid. Okay, so now we've got a cation that is weakly acidic because it's the conjugate acid of a weak base. We have an anion that is weakly basic. It's the conjugate acid of a weak conjugate base, pardon me, of a weak acid. So now the question is, well, who wins, right? Who's going to be more acidic or more basic? And this is going to come back to the Ka and the Kb for the two, right? So what I'd be looking at here is the Ka for my cation versus the Kb for my anion, okay? And so to determine these guys, again, I have to know the Kb for ammonia. So if I look up the Kb for ammonia, I find that it is 1.8 times 10 to the minus 5. So when I use my Kw equals Ka times Kb expression, I can solve for the Ka for ammonium, and that ends up being 5.5, or maybe 5.6 times 10 to the minus 10th, okay? Then I do the same thing for hydrofluoric acid. I look up the Ka for this acid, which is 6.8 times 10 to the minus fourth. And then I compare that, and I use that to determine the Kb for fluoride, which is 1.5 times 10 to the minus 11th. Okay, so now the question is, who wins in this battle? Is NH4, is this a stronger acid than this is a base? And again, how would we know? Well, we would compare the K values, right? So Ka of 10 to the minus 10th is larger than the Kb for 10 to the minus 11th. This means that this is a stronger acid than this is a base, and so because of that, the solution is going to be acidic, because NH4 wins in this battle and makes the solution slightly acidic. Its Ka is larger than the Kb of the fluoride ion. Okay, so that's a lot. I know, a lot to take in. So practice is probably going to be important with respect to these types of problems. So you will be able to expect on the quiz a problem like this where I give you a solution of a salt and I want you to tell me if it's acidic, basic, or neutral based on the information available to you. Okay, so good luck, have fun, study hard or something.